Hello, hello.
Okay, start.
Okay, we can say that again.
Good start. We're finished with our meeting.
Okay, I'm going to click to share, and then
Yeah.
we'll continue.
Okay.
Okay, ciao.
Want to drag a couple chairs over in here, for any better view? Got room.
Somebody can come sit up here if they want. There's a couple chairs up here.
Even use them.
There we go.
Yeah.
Okay. All right,
You
guys.
can now see my screen, I think. Since I can't hear anything, if I move my mouse across the screen, can you see it move? So I'm sure I'm on the right screen. It says I'm sharing. Okay, thank you. Thanks, Larkfield. Okay, my name is Fred Harris. I design radios, and I've been doing it since I was a little kid almost. And in fact, I got what's called an IEEE Fellow based upon my contribution of signal processing to the radio design. And that and $5 will get me a cup of coffee at Starbucks for the value of a fellow. So this is part of a talk I gave. Let me see if I can bring it up. In Krakow a number of years ago. I used to travel all around the world giving talks about signal processing in radio communications. I've been to MI5, I've been to NSA, I've been to the Canadian version, I've been to the Australian version of these organizations. And I've convinced people that we don't want to build radios the way we used to build radios. We want to build them using signal processing. So I'm going to share with you the evolution of my understanding, and that'll be about an hour's talk today. And then I would like to then rearrange for a second meeting later on where I talk about the details of what goes into a modern DSP-based radio. So here we go. And I did this in 2008. At that time, I was at San Diego State University, and now I'm at University of California at San Diego. Leaving San Diego State to go to UCSD 8 years ago after teaching at San Diego State for 50 years. So here is my first slide. It says transform your tomorrow. Don't know what that means. I have no idea what that is. This is my picture of my school. How did that happen? Transform your tomorrow. Oh, come on, guys. Screen sharing. There. I think we're okay now. We all benefit from wireless. So I'm going to read these words to you. And here's a bunch of birds sitting on a wire. And they all say, I don't know about you, but I'm not rooting for wireless technology. So almost all of us benefit from wireless. And this was a cartoon I found. I sprinkle cartoons all over my presentations. I once had a visitor who spent a year with me. And when I asked him before he went back to Japan what he learned, potential scam, ignore it. He said he found out it's okay to pick up pennies you see on the street. I do that all the time. And he said it's okay to inject humor into your presentations. So here's the rest of my humor. It appears to be a new wireless technology. And I worked with a guy used to come out of MIT, guy named Don Steinbrecher. He had a company called Steinbrecher. And Don and I used to build the world's best radios. They were the radios that when people showed me a spec, they said, "Can you build a radio like that?" I said, "Yes, we do it all the time." It's sold under the brand name of Steinbrecher. So Don sent me this cartoon once, which was a Xerox of a Xerox of a Xerox, and I meticulously and slowly converted it into what the actual figure was. What does the customer want? No matter what you told the customer heard you say more bells, more whistles, more dynamic range, more options, more knobs, more things I can switch on and off in the radio that you're going to sell me. So that's what Don sent me, and I redrew the picture so it was readable. And I subsequently found this came out of the New Yorker magazine. So I should have known about it, and then I would have just Xeroxed it. I used to teach courses at Motorola in Schaumburg all the time. And when I was showed them this slide, they said, there's something missing. So I had to go back and add what they thought was missing. Not only does the customer expect more and more and more and more, they expect to pay less and less and even less. And this particular little section here, less, 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 is in dollars. I have a version of this in yen and in euros and in pounds sterling, depending upon where I give the lecture. Again, compliments of Motorola. When does the customer want it? They don't want it next week. They don't want it tomorrow. They want it now, which is one of the reasons we do DSP in radios. You can bring more capability at reduced cost in a shorter time to market. If you're in business, those are all important considerations. And then Motorola also pointed out there was a slide missing, so this is the last slide. What size does the customer want? Not the big size, not the small size, but the tiny size. Look at your cell phone to see what we mean. As technology has evolved, the cell phone, which used to be the size of oh goodness, what would you call it? A carton of milk. And now it fits in your pocket. You've got one somewhere. All right. So now we're going to do a short history of communication systems. We have a better appreciation of where we are when we remember from where we started and how far we've come. Early communication at the distance, call it free space. And free space used to be acoustics and optical channels, drums, whistles, cannon fires. This was basically the optical telegraph that was built in England when England was expecting an attack from the French across the English Channel to England. And this allowed them to identify where the coast was being monitored, and they could then send messages down to London about where to send the army that's supposed to meet the French. And then there's smoke signals and semaphores and beacons and heliographs, all communications at a distance. During the Great War meant World War I, carrier pigeons were also used to communicate at a distance. I made up this slide once when I was trying to put in perspective, when did radio start and where are we now in about the modern era now? And you can see where things occurred. There was Maxwell and Hertz and Marconi, and we broadcast audio, and then the transistor came along, and Shannon and television was basically the next step in the advancement of technology. DSP, and that's where we started interacting in the late 70s of how do you build inexpensive communication systems. Oh, I also noticed that 1940 was a good year because that was the year Mrs. Harris's firstborn, that's me, came upon the scene. And that's me. Okay, milestones in electromagnetic communications. It goes all the way back to someone who came out of Denmark, Hans Christian Ørsted, who observed that if current flowed through a wire, there must have been a magnetic field related to the current flowing through the wire because it reflected a compass. And then as we developed more and more understanding of early electronics, we eventually got to the spot where we then got into the region we now call modern radios. And Edward Armstrong was an important contributor to the very early days of radio communications. The regenerative receiver, the superheterodyne receiver, and frequency modulation. But the superhet is the one that was so important to us in modern radio design. Disruptive technology, 19th century. The three things needed for this destructive technology to influence the modern era was electromagnetism, the ability to generate and store electricity, and the Industrial Revolution to build the infrastructure needed to have modern communications. Fun things to know. 1831, Joseph Henry invents the telegraph. In 1843, Samuel Morse invents and lays the first long distance electric telegraph between Washington, D.C. and Baltimore. Cyrus Field, he laid the first transatlantic cable. And we'll make a little comment about that. And there's a picture here of a great big boat called Brunel's Great Eastern. And I'll talk about that just for fun. Alexander Graham Bell, the telephone. Almond Strowger invents the automatic dialing system. Great story to tell about Strowger. They call them Strowger switches. Strowger was an undertaker in a small town in Ohio that had two undertakers. And he noticed that when people died, almost 90% of the people who were looking for an undertaker called the opposition, the other undertaker in town. And he finally traces down to the fact that the telephone operator who operated the phone in this little city in Ohio was the other undertaker's wife. So that's why the undertaker was getting so much of his business. And Strowger essentially invented what's called the Strowger switch. It's a relay with many, many, many contacts, tick, 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 which allowed automatic dialing with a modern telephone. Okay. Early electronics. Well, early electronics, there was no electronics. We had to invent it along the way. And this was an attempt to use electricity to communicate between distances. It had a battery. It had a little tank with water in it. And what happened when you connected the battery to one of the wires, you get electrolysis at the other end of the wire, and little bubbles would come up. And those little bubbles indicated, oh, they're sending me the letter L. And they wait for a little pause, and then bubbles come up somewhere else. And lo and behold, you can send letters sequentially because you had a different wire for every letter and every number, like on a modern keypad. This is called the Cook-Wheatstone telegraph, just for fun. Again, an attempt to use what we understood about magnetic fields and wires with current flowing through it. You had a little keypad, and when you press the key would then deflect a magnet in the X and Y direction. And this one, for instance, is pointing along this row, and this is along that row. So you're pointing to the letter H. And that was called the Cook-Wheatstone telegraph. 2 out of 5 coding. Now, 2 out of 5 coding is only 20 letters, so there were certain letters missing, and numbers were different than letters, and there had to be sort of a keypad, a shift key, to say it was switching from numbers to letters. So this is what one of the Cook-Wheatstone telegraph systems looked like in 1850. And basically, it's a magnetic deflection of a compass needle. And then we did some source coding and we converted a binary deflection of the needle left or right for long or short amount of time to basically cover the alphabet and all the letters plus some control signals. And that was called the Cook-Wheatstone Bridge. I bought this thing. It happens to be a Cook-Wheatstone telegraph from an antique store in London because I used to spend a lot of time in London. I spent a sabbatical there. And I bought this thing and brought it home and I proudly showed it to my wife and I said, we're going to display this in our living room. She said, not in my living room, you're not. So it now sits on a shelf near my desk in my school office. That's our version of the Cook-Wheatstone telegraph. Come on. All right. Telephone. Modern, we're going through the evolution of electronics and communications. When Bell invented the telephone, he offered it to Western Union, which was a telegraph company, for $100,000. And the president of the company had his engineers test the telephone to see if it was worth buying. And when they reviewed the telephone, part of the response they gave to the president was, technically, we do not see this device will ever be capable of sending recognizable speech over a distance of several miles. Bell wants to install a telephone device in every city. The idea is idiotic on the face of it. We do not recommend its purchase. What they should have done is bought the patents and buried them so we wouldn't have telephones. We would have modern telegraphy, digital telephones instead of analog telephones. So this is the mistake that the telegraph company made. And as a function of time, between 1877 and 1906, we went from 5 phones to 7.5 million phones in the United States. Now we're getting to where we want to be, modern communications by radio. Now, early communications was basically on and off keying. So it was basically telegraphy without wires. And they called it wireless as a result, or sometimes called radiation, electromagnetic radiation. Marconi was a very early contributor to the advancement of radio waves. I was once at a conference in Italy, and we were driving past what I knew to be Marconi's home in Italy. And my wife suggested, well, we should go visit the museum, the Marconi Museum. And no one at the museum speaks English. So they don't like to let Americans in because Americans don't speak Italian. But I had an Italian student who called for me and arranged for me to come in. And they said, well, let him stay for an hour. Well, when they understood that I knew Marconi was not the name of a fancy spaghetti, they fell in love with me because I used to give lectures on the history of radio. And they kept me there for 6 hours. That's when I had to fight my way out because they wanted to show me everything they had in the museum. Great, great trip if you're interested. Okay, the players, wireless, radio, analog, digital, DSP-based radio, software-defined radio, and cognitive radio. All of these are along the way as radio went from wireless to, we'll call it SDR now. Cognitive radio is radio that's smart enough that it can be automatically reconfigurable to the environment in which the radio is embedded. If it has to look for an empty frequency band, it can do it by itself without being told to do so. Okay, it starts with Hertz, Heinrich Hertz. He built the first radio transmitter, first radio receiver, and basically he arranged for sparks to generate electricity by a high voltage um, back EMF interrupting current through an inductor to generate a charge you could put on these balls. And when the charge got high enough, it would strike an arc and the electricity would flow back and forth. And when electrons are accelerating left and right, they emit radio waves. Then he built a receiver. And when those radio waves crossed the receiver, we induced a voltage which is high enough to induce an arc across the receiver. So he demonstrated you could indeed transmit and receive a radio wave. When asked what this was good for, his answer was no practical application. It just proved that the radio existed by virtue of the what the mathematics predicted. So this was a modern radio at the beginning. An interrupting current, and the interrupting current would generate a spark. The spark would propagate. The coherer was sort of a fancy way of building a reactive component or a passive component, which could change impedance when it saw a spark or an electromagnetic wave. So it was basically metal filings in a vacuum, and when they intercepted a magnetic wave, electromagnetic wave, the impedance would drop rapidly, and current would flow through it. But it wouldn't respond and go back towards high impedance unless you shook the glass container containing the metal shavings, and that was called a coherer. And the coherer allowed electricity to basically vibrate the glass tube to break it from the coherence to be incoherent again, so that we could then detect the signal. As long as the signal was present, it would vibrate. Signal not present, it would stop vibrating. Morse code, spark gap. So this is what a coherer looks like. Here's a physical one. And this was an instruction I found in the Copenhagen Museum. I got my PhD in Denmark, so I spent a lot of time in that part of the world. Cold, a lot of very, very blonde-haired ladies. If you weren't a blonde-haired woman in Denmark, they knew you were a visitor. Okay, and here's our friend Marconi, first transmitter, famous picture, transmitter and antenna. And this is what the system looked like. You would basically have current being self-interrupting through a big inductor. We then could transform that into a system where a spark would be generated. It would cause current to flow in this little tank circuit. And we would then broadcast. And here I put a diode in to be a part of the receiver, and you could receive Morse code. Okay. Navies fell in love with the radio, and they fell in love with the radio because it allowed you to communicate with ships at sea. Once a ship crossed the horizon because of the curved Earth, you couldn't communicate with it any longer. And when they found out you could do it with a radio, they started building radios that went aboard ship. And to this day, they still call the radio operator aboard a ship Sparky, because Sparky operated the spark transmitter. This is Marconi's tower. This is the one that was in New York, a 2-kilowatt transmitter, basically generated lots of sparks, and those sparks would be coupled through the air to generate transmitted signals. I'm going to skip that. Great story about the Eiffel Tower. The Eiffel Tower was built for the Industrial Exposition in 1889, the 100th anniversary of the French Revolution. The Parisians hated it because it was a big, ugly, unattractive thing in the middle of the city, which didn't match any of the architecture. There was a famous editor of a newspaper who always wrote these terrible descriptions of how unattractive the Eiffel Tower was in the middle of Paris. But he had dinner or lunch every day in the cafeteria in the Eiffel Tower. And when asked why, if you dislike the Eiffel Tower so much, are you having lunch here every day? He said, it's the only space in Paris where I can have lunch without seeing this unattractive device. The system was let's see, how should I say it? Before the Eiffel Tower was built, the tallest man-made structure in the world was the Washington Monument in Washington, D.C. This thing was twice as tall as the Washington Monument, and it held that title for the tallest man-made structure until 1930, when it was Chrysler Building that was built in New York. Eiffel wanted to keep the tower. It was scheduled to be torn down so people could buy the steel, for the steel was worth more than the tower was as an attraction. But what saved the Eiffel Tower was Marconi's radio, because the French military put radio receivers and later radio transmitters on the top of the Eiffel Tower. Since 1908, it's been transmitting and receiving radio and TV signals. And you can get online, look up Eiffel Tower and Marconi to see that the Eiffel Tower would be gone if it weren't for Marconi. Okay, we're back to another Danish inventor, a guy named Valdemar Poulsen. And what Valdemar Poulsen found, that if you take a plasma, and this plasma is basically electrons flowing through a gas, and if you raise the voltage across the plasma, the current goes up until the density of the plasma gets dense enough that the electric field from the plasma isolates the gas, which has been ionized, from the external voltage. So when the voltage goes up, the current actually goes down. And Poulsen made the observation, if a positive resistor takes energy out of a circuit, then a negative resistance should put energy back in the circuit. And he was right. So he built the first continuous arc transmitter that could transmit continuous signals. And you need continuous signals to transmit basically audio. Okay. So this happens to be, so here's an arc. Now, when you have current flowing through the electrodes of an arc, what the current does, it vaporizes the probes. And if you vaporize the probes, then you have to replace the probe. So it's like a welding torch. So what they did is they put the welding torch in an inert gas, nitrogen. And if you have the nitrogen in there, that will cool the rods so they don't vaporize. The problem is, what was the problem? Oh, you had to carry the heat away from the electrodes, otherwise you get local heating. So it was circulating nitrogen, but if it was circulating, it would carry the arc with it and break the arc. So they used a magnetic field to keep the arc present where the electrodes were, while the gas was carried with the heat generated by it. And that's what a Poulsen generator looked like. Poulsen, incidentally, is known as the inventor of magnetic tape recording, for what it's worth. And this one happens to be a 500 kilowatt Poulsen arc transmitter. So arc transmission is different than spark transmission. Sparking was a way to build basically an RF wave with basically current flowing through the arc, which act like a switch. Through a spark, which act like a switch. But the arc was sort of basically a negative impedance in parallel with the tank circuit. The tank would break into oscillation. And what they did, they keyed the tank to change the resonance of the tank and get a FSK modulator out of a continuous RF wave. Isn't that neat? Okay. U.S. Navy bought thousands of these and put them aboard ships all over the world. before electronics allowed them to replace generators based upon an arc with vacuum tubes based upon the conditions for oscillation. Lee DeForest. He was sort of a dishonest man. He stole a lot of things. Among the things he stole was what's called the Audion, which is basically a diode with an extra lead in it. And this lead was called the grid. And the grid could then modulate the amount of current leaving the cathode and going to the anode. And that was basically now the modern triode. Okay. This is an issue, a set of stamps issued by the U.S. Post Office. You can tell how old it is by the fact they're only 20 cents. I have no idea what a letter costs to send anymore. But there are a number of people in here. Steinmetz, which has a sine wave coming out of his ear. Edwin Armstrong, Philo Farnsworth, inventor of television, and Tesla, who basically built an AC motor. In the early days of electricity, the question was who would win, Westinghouse or Edison. Edison wanted to use DC, and Westinghouse wanted to use AC. And it looked like Edison was going to win because you needed DC to convert electricity into mechanical motion. And the story goes, it's a joke, but it's a huge story, that Westinghouse calls up Edison one day and says, I win, electricity will be distributed as AC instead of DC. And the reason that's true is Tesla built the first induction motor, a motor that could run on AC. You didn't need DC to convert electricity into mechanical motion. Edward Armstrong, known by the general population as the man who invented FM radio, but more importantly to our discussion, he invented the heterodyne, the superheterodyne receiver, which is the core of almost all modern radios until he hit the software defined radio or DSP based radio. There's Armstrong. This is the regenerative receiver he built. And what the regenerative receiver said, I'm going to take a vacuum tube, there it is, put some feedback around it, and bring it to the very edge of oscillation. And when electromagnetic field pumps some extra energy into this little tickler coil, it breaks into oscillation. So suddenly, this becomes a very, very sensitive amplifier, which can detect signals after an amazing amount of attenuation, amplify them, detect them, and then convert them into audio if we follow the rest of the design. You might want to read the article about how Armstrong and Sarnoff interacted in the early days of radio communications. And I put this joke up to acknowledge my brother, who was a collector of radios. And this thing says, and I got this radio from a farmer for 3 packs of gum. And the little lady is sitting there saying, I should have known better when he told me he was a radiologist. Okay. Now, in the early days of radio, the super regenerative radio receiver was very sensitive to, let's say, the electric field in a room. If you walked across the rug, the radio would turn on. If you rubbed the cat, the radio would turn on, because it was at the very edge of saturation, and it didn't make of oscillation, and it didn't make very much change in the electric field around it to break it into oscillation. So to get away from that, we invented something called the tuned RF. And the tuned RF basically is multiple stages of amplification and gain amplification with tuning. And you can then tune each stage of the radio. And if you tune them all to the same exact station, you got a product of all the gains, which will then allow you to receive a signal. And now you can also tune a signal to be at different center frequencies. And once you tune the radio to a station, you say, don't touch it. I like that station, because it's hard to retune all the separate stages to exactly the same frequency. That's just fun to know. Now, these are just fun little comments I'm going to make. This is a picture of an old Atwater Kent radio, which happens to be a commercial version. Oh, incidentally, in the early days of radio, you couldn't go to the store and buy a radio because there was nothing to do with the radio except play with it, be an amateur radio person. So they would buy all the pieces and take it home and mount it on a board and then connect all the pieces together. And the question is, what board could you mount them on? Well, Mom had a board in the kitchen. It was called a breadboard. And you can then mount all the pieces on the breadboard. And still today, they call the process of building your own circuit on a chassis the breadboarding process, because that's the way we used to do it. Okay, so this is a commercial radio. It's got all the same parts. And if you could look inside, you see you get multiple pictures of this guy. Where are we? With different tune circuits, multiple vacuum tubes, a final tube with a detector to convert it back into audio. Okay, so that's an Atwater Kent Model 20 for what it's worth. It works out my daughter's husband, um, um, Jorge, happens to have the compliments of my brother Matt, an Atwater Kent Model 40. And this happens to be an Atwater Kent radio, which only has one knob on it. And now the ability to build a radio with only one knob is actually compliments of, oddly enough, Armstrong again. Armstrong built not the super regenerative receiver, but also the super heterodyne receiver, where you could move a signal from one place to another. And instead of moving the filter to where the signal was, you move the signal to where the filter is. Now, as soon as he did that, and he sold the patent to Sarnoff at RCA, and RCA would not license that radio design, every company that built radios went out of business, because you could not sell a radio with three knobs that needed to be tuned, against the radio that only had one knob. And I saw this Atwater Kent radio years and years ago at a ham radio festival at Virginia Tech many years ago, because I spent a lot of time at Virginia Tech. And they showed me the radio. It only had one knob on it. And I said, I know this predates, this is following the Armstrong Superhit. So how do they build a radio with one knob? So I asked them to open it up and show me the inside. And there it is on the inside. And look, there's the three tubes and three sections, 1, 2, 3. It had inductor, and three tunable capacitors. And what they did, this little knob had a linkage, a gear linkage, where one knob turned all three knobs. Well, you see, you didn't have to. So they were trying to get around the patent by marketing a one knob radio to compete with basically the radio that Armstrong built, we now recognize as a super hit. Isn't that neat? Okay, early mobile communications. You shouldn't drive while you're on the cell phone. It's not safe to do so, as you can easily see. Okay, this is the super hit. This is a modern picture of it. Instead of having a bunch of tunable stages, the stages were all fixed at an intermediate frequency. You had a filter, which is called an image reject filter, because when you go through take two tones and add them together and go through a nonlinearity, you generate the sum and difference. What this guy was supposed to do is get rid of the sum frequency or let the difference frequency through. And then you had a tunable circuit where you could tune the local oscillator to be a fixed distance away from the signal you wanted to tune to. And in this example, you had a signal at 1 megahertz. You had a local oscillator at 1.1 meg. And lo and behold, when you go through a mixer, what came out of here is a signal which was 100 kilohertz, and that went through the rest of the receiver chain. And this is a drawing lifted from the original 1918 patent that Edward built, and he built it for the U.S. Corps of Engineers during World War I, when they were using telephone lines, and he needed a radio to listen for approaching airplanes because the engines on an airplane emitted RF, and it was an attempt to build an early warning system to protect people from a threatening aircraft. Neat little trivia. Okay. Ta-da. Okay, the modern era, we're getting close. You want to get rid of vacuum tubes. There's the vacuum tube. And replace it with a transistor. And these are the people who got, oddly enough, the Nobel Prize for inventing the transistor. And we want to get rid of it because while the vacuum tube worked, it had certain disadvantages, high voltages, lots of current, lots of power, because you needed thermionic emission of electrons. The modern era starts. Jack Kilby working for TI, Robert Noyce working for Intel, simultaneously invented the integrated circuit, putting multiple transistors on a single substrate and then interconnecting them with internal connections on the substrate so you didn't have to wire them. They got the Nobel Prize, and the only Kilby got it because when the Nobel Prize was awarded, Noyce was dead, and you can't give a dead person a Nobel Prize. But Kilby acknowledged the fact that he should have shared this with Noyce. Ted Hoff is a guy I worked with at a patent infringement case, working against, oddly enough, a radio. And it was the radio designed for high definition TV. And so Ted Hoff actually was the designer of the first integrated, what should I call it, computer. He built the first system for Intel, which was basically a calculator which only had one chip in it, and that one chip operated the keypad, the display, and did all the arithmetic. And he got a Nobel Prize. He got what should I say? He didn't get a Nobel Prize, but he got an award that he's in the American Institute of Inventors Society. We were once in a patent infringement case, and when asked what makes you qualified to be an expert witness here, he said, I invented the computer. I invented a microprocessor. That's what it was. And I thought to myself, yeah, but he did. I went and checked. And they had the inventor of the microprocessor basically testifying on a radio design. They had the wrong guy. I was the right guy to have for that particular testimony. So we won. Okay. Gordon Moore. Gordon Moore made the observation that the cost of building electronics and was for a given amount of electronics, the cost was going down about 50% every year and a half. Or the cost for the same cost, the amount of electronics you could put on a chip for the same cost was the same every time the year and a half went by. You could double, 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 double. And that's called Moore's Law. And Gordon Moore made an interesting observation at a particular conference. He pointed out that we all own 1 billion transistors, and that he also made the observation that, this is simply talking about 1 billion transistors. Oops, where are we? Okay, if you had 1 billion transistors, if they were dollars or banknotes, 1 billion banknotes would be a stack 76 kilometers high. And a billion seconds is 32 and a half years old. So if you are alive for 32 and a half years, you lived a billion seconds. If you are working on your second billion, you will get there when you're about 70 years old, 65 years old. Okay. For comparison, the Eiffel Tower, which only has 18,000 parts, was a pretty impressive device with 18,000 parts. So imagine what you could do with a billion of them. Okay. Again, compliments of Gordon Moore. At a particular conference, he made the statement that the world manufactures more transistors than it grows grains of rice. Now, if you've ever been in Japan or in China or even in California, where we grow lots and lots of rice, we have a lot of rice growing, but a single transistor, a single large silicon wafer can have more than a billion transistors on it. And a billion grains of rice, for what it's worth, a billion grains of rice took me hours to figure this out, is a box about 32 cubic meters, or a room about 3 meters on its side. It would weigh 24 kilograms. And when I did this in 2008, it would cost $26,000. My Mercedes weighs 2.2 kilograms. So that means a billion grains of rice would be about the weight of about 13 Mercedes grams, Mercedes Benz. And well, again, compliments of Gordon Moore that a transistor in the early days might cost $1 to build a certain transistor. And in today's world, a transistor, come on, where are we? Um, uh, a dollar would give you, there we are, $20 would give you a billion transistors. Desktop computer, notebook computer, handheld device. Darn, I can't find my grain of rice computer anywhere. Oops, I may have seen it was a broccoli this morning. That's my jokes. Last joke. It's all done with computer chips. Okay, we're getting into the modern era. Harry Nyquist, the sampling theorem. The sampling theorem says if you give me a band limited signal whose bandwidth is limited to some interval, then I can take samples of that wave shape. And if those samples are close enough together, I can rebuild with arbitrary precision the details of the continuous band limited signal from the uniformly sampled samples of that signal. We call that the Nyquist theorem. Now, in order to do what I just described, you need something that converts an analog signal into a digital signal. So here we have it. If you didn't know what an analog to digital converter is, sometimes called an ADC or A2D, analog to digits, this is an A to D converter. It's a big machine and you put A's in on the top and it goes ka-chunkity chunkity chunkity chunk and D's come out on the other end. This came out of an IEEE article in the IEEE Los Angeles IEEE section. And I thought, and it was a black and white, and I colored it by hand. I thought, I have to use that in the class somewhere, an A to D converter. The neat thing about an A to D converter, it's reversible. If you run it backwards, you can take the D's, pass it in, turn the machine upside down, the converter them back into A's for you. And that's your digital to analog converter. Just so you know, they're a reversible process. Okay, now we're going to talk about radios. Where do we start? Bear with me. Later on, the next time we meet, I'm going to show you what goes in the radio, but I'm going to show you the high points now. Here is the regenerative receiver, Nyquist again. Not Nyquist, Armstrong. So it's a regenerative receiver sitting at the edge of oscillation. It breaks into oscillation if it intercepts an electromagnetic wave. It's prone to break into oscillation when the cat walks across the room. So to avoid that oscillation, the tubes weren't good enough to give us good linear gain. But if you had lots of tubes in cascade and you tuned each tuned amplifier to the same frequency, you got a TRF tuned radio receiver. And then finally, a detector, and you convert it back into audio. Now, there's an important consideration here. The tuned RF was an attempt to build a low-cost, high-performance radio receiver, and this actually did quite well for a while until Armstrong came around again. We're back where we started. And what this is a signal comes in, and what Armstrong did, he said, instead of taking the signal and sliding the amplifier to where the signal is, we'll leave the amplifier at a given frequency and slide the signal to where the amplifier resides. So this is the heterodyne. Hetero means different. Dyne means move. We're going to move the signal of interest from one place to another. And once you get the signal at a given frequency, it goes ka-chunk, 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 and they get through the intermediate frequency bands, and then you can detect it and then listen to it. Now, in the early days of radio, it was double sideband with carrier. You inserted the carrier to the modulated signal because you needed a copy of the carrier at the receiver to successfully demodulate the signal. Now, in a modern radio, the carrier contains about 95% of the energy in the transmitted signal. 95%. So if I had a 100 kilowatt transmitter, 95 kilowatts of that is being carried along with the modulated sidebands to basically run this diode at the receiver. That's all he's doing, 95 kilowatts. When you started building battery-operated equipment, we said we can't do that anymore. So we've got to be able to build radios that don't rely upon the carrier being present in the receiver. So instead of saying, please send me a carrier, we said, oh, never mind. I'll just build my own. So this is the Armstrong front end. And now here's the IF strip. And now we're going to do something interesting. We're going to down convert the IF to baseband. Don't use the diode, but use two diode detector or two down converters. Now these down converters, happen to be called mixers. So there's a mixer here and a mixer here. There's a filter here and a filter here. These are analog devices. And if you give me a point in two space, and a point in two space gives me a angle, and if I can measure the angle, I can answer the question, tell me the rate of spin of that angle. And if I know the rate of spin of that angle, I can reconstruct what the carrier is. And that's called double sideband suppressed carrier. Now, the problem is an analog filter and an analog filter, an analog mixer, analog mixer. In the analog world, a circle with an X in it is called a mixer. In the digital world, a circle with an X in it is called a multiplier. Important difference. So here's a case, two parallel analog paths, two mixers. And what this is supposed to do is take the product of the input signal with a locally generated oscillator to down convert a signal to baseband. And you want to down convert a signal on a cosine carrier and on a sine carrier. And if you have a point in two space, you can measure the angle and determine the rate of change of that angle. And then you can use feedback to control the center frequency of the oscillator. And you can also use feedback to run a clock so that you can down convert the signal from analog to digital data. The problem is the problem is we don't know in the analog world how to do multiplication. We do have something called a four-quadrant multiplier. And what the four-quadrant multiplier does, it uses bipolar transistors to take the logarithm of a signal, add the logarithms, and then puts the bipolar transistors in a feedback path to do the inverse log exponentiation, and you can add logarithms together. The problem is they're too noisy. You can't use them at the front end of a receiver. So in order to do the down conversion, we use square waves. And the square waves operate something called diode ring modulators. And a diode ring modulator forward biases and back biases diodes. And you get a square wave out. And by properly phasing the two square waves, the fundamental frequencies are a cosine and sine. But they also have third harmonic and fifth harmonic and seventh harmonic distortion, which you have to suppress because they think they were invited to the party. So the reason we like the digital world, we don't use mixers, which are really not multipliers. They're switches which turn things on and off. Okay. So what we do is we take the signal and run an A to D converter and go into digital land where now we have multipliers. A circle with an X in it is really a multiplier. And the neat thing about two multipliers, they have exactly the same gain. The filters will have exactly the same gain over time, temperature, and frequency because there's no tolerance in a DSP-based filter. No tolerance, there's no efficient, no filter built out of 5% components. And when you build a filter, let's say with a dozen inductors and capacitors and resistors, and they have 5% tolerances, a certain fraction of them will be out of spec. So here's the problem with this circuit. This path and this path, both of them the same, this path, there's an imbalance between gain and phase of the two paths. And if you have an imbalance, you break the orthogonality of the in-phase and quadrature signals called cosine and sine. A real embarrassing awareness that when you have an analog path, two paths in parallel, I guarantee, money on the table, guarantee the two parts are never the same value. And if they're not the same value, you have to accept a tolerance, a spread, and that spread you can test with Monte Carlo techniques to see when the filter will meet your specifications. In the old analog days when we built radios with analog devices in them, we had potentiometers, and the potentiometers were used to adjust and balance the imbalances in voltages and impedance levels and signal strengths because of the tolerances in the analog parts. One of the things you'll find in the modern world, here's the modern world, analog mixers, analog filters, two converters because they're still analog. They are not the same value. The tolerances of these guys are such that the dynamic range of the radio is limited to about 30 to 35 dB. If you build a system with tolerances in them, 30, 35 dB is the best you can get between in-phase and quadrature effects on the performance of the radio. If you do it in digital land, where there aren't any tolerances and there aren't any potentiometers, you look at a modern radio, open up your cell phone, open up your anything, there's no potentiometer anywhere on that circuit board. And why is that? Because when I build something out of a digital DSP-based anything, there's no ability for that system to misbehave. If it's going to run at 10 degrees centigrade or 100 degrees centigrade, or it's going to run at minus 100 because I'm running in the Arctic, it's going to be the same behavior no matter where you build it. Interesting reason. of asking the question, why DSP? It's because we want to get rid of potentiometers, as strange as that sounds. Okay. Now, the problem is in this little circuit where, oops, here we are. We take the IF strip, we down convert, and if you down convert, there's an imbalance. This system is low performance immediately. So what you can do is this. You take an A to D converter, you convert it to digital end, and then you can now do down conversion and filtering and not worry about tolerances stacking up to reduce performance of the system. Nobody, if you are in this radio business long enough, nobody can build a radio with 100 dB dynamic range using only pure analog devices. Period. Bang. There is no such thing as 100 dB. Now, you can if you're a high-end designer. If you're building radio telescopes, you can get a 200 dB dynamic range. But what you do, you put all the analog components in liquid helium to make the noise temperature be so low you can avoid the tolerances and the effects of the thermal agitation caused by electrons bouncing around inside of crystals. Okay, now notice one of the things we do here, once you're in digital land, you can use that to adjust the clock. You can use that to adjust the mixers. And you can then use that to adjust the interpolators here. So you don't need to build variable filters. You can build a variable filter by using an interpolator. So now you have a free running clock. And now once you're in digital land, if you believe that Nyquist is right, if you satisfy Nyquist, the samples that you have contain all the information of sufficient precision to reconstruct the original analog signal based upon the samples. Now we're in DSP land. Okay, almost there. Show begin. A modern communications, you have bits, you convert them into wave shapes, put the wave shapes through the channel, pull them off the channel, demodulate the wave shapes, convert them into bits. It works out, one of the things that the channel does, it attenuates the signal. And the signal goes like 1 over r squared in strength as r gets bigger and bigger, as distance gets further and further away. The first thing the receiver must do is get rid of that attenuation. So it puts an amplifier in, called a low noise amplifier. And what the low noise amplifier does, it takes the attenuated signal, brings it back up, where the signal strength is big enough that you can now put it inside circuits. Now, when we look at the output of the low noise amplifier, we say, look, there's noise here. And what we do, we blame the noise on the channel. So we say, well, the channel is band limited and it added to white Gaussian noise. I was an electrician when I was in high school and college, so I thought AWG was the American wire gauge. When I started building radios, it stopped being the American wire gauge. It became added to white Gaussian noise. Now, the noise didn't come from the channel. It came from the amplifier, undoing the attenuation caused by the channel. So we blamed it on the channel. Because if you didn't have the attenuation, you wouldn't need the amplifier. And since you need the amplifier to see the output of the channel, we blame the noise on the channel. Okay. And it's white noise because the power spectral density is a constant across an amazingly large bandwidth, and the amplitude distribution of the noise is on the in-phase and quadrature component Gaussian distributed. So AWG is the name of the game if you're fighting modern communications. I'm going to skip this. We have non-regenerative and regenerative repeaters. What a non-regenerative repeater does, it takes the signal off the channel, and when you come out of the amplifier, you see the noise. And then what happens, you pass that into the channel again, and it too adds noise. And you pass that into the channel again, and it too adds noise. So if I was crossing the United States, I might take 100 amplifiers, and each amplifier is added its own noise. In a regenerator channel, you estimate the signal and rebuild it and throw away the noise. And then you throw a fresh signal in and you rebuild it and throw away the noise so you don't stack up the noise in a regenerative repeater. And if you do that, I'm going to can't skip this slide, it's too important. A student once came to me, he said, I know why we do digital communications. He said, Sermon on the Mount, Matthew chapter 5, verse 37. If my life depended upon it, I couldn't have told you what that was, but I'll tell you what it says. It says, but let your communications be yea, yea, nay, nay, for whatsoever is more than these cometh of evil. Let me interpret that for you. It says, if you want to do good high level communications, use binary communications and use redundancy, because if you use redundancy, you can strip away the noise and recover from noise induced by the presence of the additive noise. Isn't that neat? So we have biblical injunction to use digital comms and perhaps use digital radios. And to paraphrase the great bard, the world is an analog stage in which digits play a big part. Okay. I'm going to skip. Oh, maybe I won't skip. This is the standard curve of what the bit error probability is if I have what's called a conditional density function. If you transmit a +1 and you receive in the presence of noise, these are the amplitudes you'll see. If you get a -1 and you receive it in the presence of noise, these are the density functions. And there's always a non-zero probability that I transmit a +1, but the tail says, gee, there's a non-zero probability I'll receive a signal as a -1. And what you want to do is make this probability so small you can ignore it or fix it with error correcting codes. Andy Viterbi is the guy who invented basically the convolutional codes. Decoders call it Viterbi decoders. And the Viterbi decoders is used as the equalizer, oddly enough, in the European early digital telephone system. And I once heard Andy was teaching at my school. I once heard him say, if your system is not making errors, you didn't design it right. See, if it's not making errors, you put too much energy in the modulator so that the tail was so short, you didn't see any errors. And you pay for that all the time by running the batteries longer and needing bigger power supplies and bigger heat sinks. And if you allow the errors to occur in your design and then fix them with error correcting codes, you only pay for the fix once. You don't pay for it a lot. So that's the reason we use error correcting codes to reduce the error from an acceptably small value, 1 part in 100, to 1 part in 100 million billion if you need to, by using redundancy to detect and correct the errors instead of using energy to avoid the errors in the first place. Okay, modulator, demodulator, almost there. Going to skip this, skip. Shannon's. I'm going to skip. I'm going to skip these and talk about the modern radio. 4 pillars of modern communication: bandwidth, signal to noise ratio, data transformations, signal transforms. That is, 3 of these are Shannon. Data transformations complement the Nyquist. You can add error correcting algorithms to the data to improve communications. Now, once you have a data communication signal, operator, you have a computer on board, and that computer can do other things for you. So let me tell you what it's going to be. Skip. want to show you an interesting problem. Don't copy an analog radio receiver design into the digital domain. If you copy it, you include compromises that were made when the original analog receiver was built. And if you copy the compromises, then you're not improving the performance. You want to include higher performance at lower cost, and you don't want to go back and include errors you made in the old analog days because you had no choice. So, for instance, in the old analog days, phase lock loops weren't easy to build. FM receivers weren't easy to build. In DSP land, they cost you nothing. So you don't want to build an analog FM receiver in the DSP domain. You want to build an all DSP-based receiver. So here's an interesting problem. Planet Earth, satellite sitting over Japan, and this satellite is beaming down basically 200 MP3 channels, 384 MP3 channels, stereo. And what they do, they demodulate these channels and then put them in giant apartment houses in Japan. And they came to me in San Diego, this group that built them, and said, we can't get the parts anymore to build and repair the old transponders we have, which take the satellite data, convert them from MP3 to FM, and then allow us to distribute them in our apartment houses. And the question was, how big a room will it take to build the DSP version of the room? And I said, well, show me what you've got. Well, this is what they had, a schematic. Schematic was in all Japanese, very useful to me. And I said, can I get any of these parts? He said, no, these are all discretes. You can't buy them anymore, but we need 285 of them. I said, all right, what does it look like? Oh, there it is. This room is basically 19-inch racks, 6 feet tall. There are 12 of the stacks here. There's 1, 2, 3 rows of these 12 columns where each of them contains nothing but transponders built out of discretes, 192 stereo FM modulators and demodulators. And the question was, well, how big a room will it take to build this? Well, first we said we have no idea how big it is, but we don't know what's in there. So they gave me the schematic, they gave me a radio, and we took it into the lab. We powered up the radio, and we probed it with an oscilloscope and a signal generator, and we reconstructed what the schematic was. And here it was. A left plus right channel, a left minus right channel, DBX. Why DBX? Because they didn't want to pay the fees needed to reimburse the company that builds the improved audio for FM modulation. Pre-emphasis, because it's FM, something to limit its bandwidth. Then a VCO, because we're going to translate that signal up to a given band. Remember, there's a left plus right channel. Normally, if it was a stereo FM, you move it up to 38K. So we're going to move this up to somewhere, 32K. And this something called subsidiary carrier authorization. All of this is in one of those receivers, and there's 293 of them. So this is what our DSP-based version looked like. The data came off the satellite, we received it, we then demodulated the MP3, converted them into FM, and then we built a single channel. And then the question was, how big a room will it take? Well, I'll show you how. Here it is. I said, I looked at the block diagram, and I think that 200 and, let's see, got to be careful. 293 channels, 290, got to double this. That's 295, whatever it is, almost 3. almost 400 channels. There we are. I think you can build all 400 of them on a single chip. And their response was, don't be absurd. You can't pack that room, here's the room, into a single chip. And I said, I think you can. And they wouldn't pay me. They wouldn't fund me. I said, I'll tell you what, if I can build one of them on a single chip, will you then consider funding me? So I built one up, and lo and behold, to build it a DSP-based radio, it's only lines of code in memory. And I could then build that. And I said, I can build one of these on the chip, and I still have 95% of the chip that's empty. If you give me permission, I'll give you all of the 294, all 400 channels. And they did. They gave me the permission to go build it. And that room, this entire room, there we are, fits in this box. And this box is 2 units high, and that means 3.5 inches high. It's 17 inches wide and 9 inches deep. This box contains that room. And we had, and this is a Xilinx chip. And we wrote a paper that appeared on the Xilinx webpage about how to pack a room of FMD modulators into an FPGA. Almost finished. And then about 6 months later, we got a Chinese version of this that came out of China. And my Chinese student knew the teacher who went to the same school he went to in China. And he said he did a pretty good job of interpreting our English and convert it into Chinese, but our names don't change very well, nor Xilinx or FPGA. There's no Chinese equivalent. I'm going to do one other or 3 other little things, and then we'll call it quits. There's a company in town in San Diego called ComString, and they used to build satellite modems. And the chief engineer asked me to come in. He said, I would like you to build a single receiver, which under software control can be our entire product line. He says, right now we sell, let's say, 20 different modems. There's a 10K modem, there's a 50K modem, there's a 100K modem, there's a 150K modem, there's a 1 megahertz modem. And we need parts in-house for every one of these modems. Just keeping parts in-house is outrageously expensive. I'd like you to design one modem, which under software control can be our entire product line. We'll take that one chip, put it in the box, and we'll change the title on the box. This is modem 600. This is modem 1 million. This is modem 5 million. Inside, it's all the same. Inside, it's one chip, and under software control, it's your entire product line. And he told me 10K to 10 meg in 1 bit per second steps. I thought he was joking. And he said to me, no, we're not joking. We're serious because we want to save money. And he said, as I was walking out of the room, it's not likely it can be done, but we know someday it will be done or can be done. He expected me to predict the dawn of the coming of the horizon so that he could be prepared to greet that horizon and do what he wanted to do, build one chip to replace his entire product line. It took me a whole week to design that radio. And this is the patent number, digital receiver for variable similar rate communication. They still sell that chip. And we used to call it RF to digits. That's the entire. It took L-band data and converted it into any binary stream of any symbol rate you want, from 10K to 10 meg on a single chip. Still manufactured. And one of the reasons we can do that is what we can do is if you want to change the bandwidth of a DSP-based chip, you must have a higher sampler rate. If you have a higher sampler rate, you need a bigger anti-aliasing filter or a broader band. But what we can do is we can pick a fixed A to D converter, sample at that fixed rate for the highest bandwidth, and then build interpolators to change the input rate to any output rate we want and not have to build any of the analog stuff in front to build variable bandwidth receivers. And we used to do that at a trade show. We'd have a truck out in the parking lot. We'd point it up at an antenna and we'd say, tell me what bandwidth you want. And we'd key it on the keyboard, and you'd watch on the spectrum analyzer the spectrum of the transmitted and received signal go in 1 hertz steps to anything we wanted between 10K and 10 meg. And I think that's all we're going to say here. There's a whole bunch of other things we can say, except to say that when you build a receiver, this is the first digital radio I ever built for Cubic Corporation. And basically, it was a surveillance receiver. So someone sitting with earphones on, tuning radio, listening to eavesdropping on someone else's radio. We could do this. And the original analog radio had tick, 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 4 different bandwidths it could receive. And the question was, how many bandwidths can we have in digital radio? It works out a digital radio receiver bandwidth is only a list of numbers in memory. If I take that memory, replace it with a different content in memory, I get a different bandwidth. So we used a thumb wheel switch with 99 different center frequencies, because all we had to do is tell the receiver, go to this block of memory, or that block of memory, or that block of memory, to take care of the bandwidth we need for the particular bandwidth of interest to the radio user. One of the guys I know at school was a ham radio operator. He had a, let's see, what was it? A Raytheon radio. I think it was a Raytheon. And he said it's the best radio in the world. And he knew I built this radio for Cubic, and he borrowed it. So he borrowed the radio and called me that night. He said, your radio is awesome. And he sold his radio on eBay the next day. And he hasn't given me back this radio. He still has it in his Radio Shack. And I think that's all we're going to say. So what we're saying is we can build amazing radios. Radios that are unbelievably high performance because we can do things that the analog guys couldn't do. For instance, if you're building a radio and you need to do the arctangent, you're building an arctangent for a phase lock loop. Well, the analog folks can't build an arctangent. We have no trouble building an arctangent in digital land. One of the things we can do in digital land that the analog folks can't do, when you make a decision, and that decision is going to guide how the radio operates, you have to tell the radio, tell me the signal to noise ratio of that measurement. If you tell me the signal to noise ratio, I can automatically tune all the systems to reduce its noise bandwidth performance to accommodate the higher noise in the current receiver. If you want to build the best radios in the world, the best radio in the world will have in it somewhere. Let's see if I can get there. Oh, here we are. Why is it going down? I have passed it. I think I'm running out of time. I have run out of time. But I do want to just show one little circuit. No, I guess I can't. Anyway, one of the things we can do, we can build a signal to noise ratio estimator in the receiver, which tells all the loops, your frequency lock loop, your phase lock loop, your equalizer, your match filter, your anything else that has to deal with additive noise in the system. It tells the system what the SNR is. And if you know what the SNR is, you know how to adjust all the gains of the loop so they stay stable all the way down to negative signal to noise ratio. At SNR, the data may be useless, but it'll never lose lock. When it comes out of the low SNR environment into high SNR, it doesn't have to reacquire. It never lost lock. That's what you can do with modern DSP-based radios. You can tune things which never have to be adjusted, never have to be balanced. Now, if there's reasons you can't do a design without the analog parts, you fix the analog parts. You build equalizers, you build cancelers, you build things which remove DC injection, you remove I and Q imbalances. So I used to do a whole series of lectures on dirty RF. How does DSP make an analog radio better than it possibly could be if it weren't for DSP? I once did a paper for the Microwave Journal 50th anniversary on DSP and microwave receivers. And someone who reviewed my paper said, why would a microwave engineer care about DSP? And the answer was, I didn't give him that answer. The answer was because Gordon Moore is coming to eat your lunch. And if Gordon Moore eats your lunch, you can't build a product which will compete with someone who included DSP to make their system better than your system. I used to go to a place like MI5 or NSA or other three-letter agencies around the world, friendly agencies, and tell them, you can't build analog radios anymore. You have to build them this way. And they all do, and they all can. The imbalances that break the orthogonality of I and Q and break the orthogonality of positive negative frequency disappear in a DSP-based system. And that means you can build radios with 100 dB dynamic range, which you have no hope in heaven's name to try to build without the benefit of DSP. So that gives you motivation for why we're here. It hasn't told you how to do it, but that's the next time we meet. And I think that's all we'll do. I'm going to stop sharing. Stop sharing, the man said. Okay. Now I can answer. I can see the audio is going out, but I don't have any audio coming back. Maybe I do.
Can you hear me now?
No. All right, you can drop me notes.
Sure.
I can call him up on
Somewhere
the
I
phone.
get
Yeah, let's
notes.
you know,
Chat.
up and then we can.
Does anyone have any questions? So what I gave you was, oops, that's me. I can see me. Okay, what I gave you is my introduction to my DSP course on software-defined radio. And now what we need is second half of the introduction.
So we're going to try this as an experiment here. This is the modern technology. Since you hear us, I'm going to pass my phone around.
Okay.
And you can ask you questions, okay?
Sure, absolutely. Okay, thank you.
So who wants
Who wants to
ask?
answer question?
Anybody?
Yeah, I'll.
Tom wants to ask a question.
Hey,
Hi,
so
Lockfield.
what sort of things would you expect for like new digital modes that like, or maybe ones that are used in professional that aren't yet used in ham radio? Do you have any like particular modes that you think would be effective that just aren't being exploited at the moment?
Well, what most radios don't do, they don't estimate SNR. And if you want an amazing radio, you got to keep the SNR in the loop. The other thing you must build an amazing amount of shield around the radio. Don Steinbrecher, his company was called Steinbrecher Corporation. He built the radios used for over-the-horizon radar. He only had one customer, U.S. government. And he eventually sold the company when the Russian Empire fell apart. But he would do the analog stuff, and I would do the digital stuff. And one of the things he told me, build your radio, stick it in the tub of water. If air bubbles are coming out, air can escape your radio. If air escapes, radio waves go into your radio. You have to shield the radio from all RF environment. That's also going to be a limiting contributor to the performance of that radio. Now, what we now will see, there's an interesting problem. We're starting to use the internet and radio communications for navigation. That is, we're putting radios in cars to avoid collisions. Now, if you have a collision avoidance, you want very short lead time. Well, if you have short lead time, you can't have long delays. If you have long delays, then it's too late. You've already crashed into the car. So the rules are changing when you start looking at systems where the radio is involved in guidance, like, for instance, collision avoidance. So we're now going to build error correcting codes of short length. And if they have short length, they can't have high performance anymore. Yeah, what Shannon said, in the limit as n gets big, you can make the error rate as small as you want. Well, now we're going to take away that option. We're not going to allow long delays anymore. The rules are changing. Radios are also now easy to build diversity. I worked on police cars, and a typical police car has four-way diversity, 4 antennas on them, and then combiners. We never want a car in hot pursuit to ever lose a radio link. I worked on the Air Force One, and the Air Force One is never allowed to lose radio link to his supersonic aircraft that are accompanying him. And one of the things we found out, 2 planes flying faster than the speed of sound are approaching each other. As they pass, the Doppler shift is so big, the radio loses link. Not allowed. One of the things I was asked to do is build a radio that will not lose link under those conditions. Wow. And we did. So you can do amazing things. And a lot of the stuff will be related to satellites. Yeah.
Anybody else want to ask a question?
Question?
Thank you very much.
Okay, yeah. Just on behalf of the club, thank you so much for this. It was such an informative talk, just I think for everybody here. Can you hear me?
Well, thank you. Well, I'd like Matt and the group to get together, fix whatever the problem is. I've lost my link, and then I'll go into the inside of what you can do in a software-defined radio that is totally different than the analog prototype. Among the things we do is you build multi-channel receivers. Every product I build now is a 500 to a couple of thousand channels aboard a satellite, all operating simultaneously at low power and at low cost. So I worked on Amazon. I worked on with SpaceX, and I've worked with other companies that are basically putting up their own satellites, and they're all high performance, ultra wide bandwidth.
Very nice. I actually get my first NBI non-terrestrial networking NB-IoT modem comes in tomorrow.
Ah, do you know Bob McGuire, perhaps? Bob McGuire used to be head of the ham radio satellite group.
I personally don't know.
Okay, but I worked with him. I worked with him at Princeton for a group called IDA, Institute for Defense Analysis. And we basically built amazing squared radios.
Okay, so
radios that were totally beyond what people thought you could build in a radio.
So It's wonderful. Thank you. Look, it's about half an hour out, so
Okay,
thank you for being our speaker today.
Yeah. Maybe we could do it again,
well,
next time.
thank you.
We look forward to part two.
Okay, so am I. It could also be a part 3. Okay, thanks all, and thank you, Matt.
Thank you.
Okay, bye-bye. Bye, Ellen.